or sit-in, hopefully crystals you'll be getting. So vapor diffusion is a method that we use in X-ray crystallography. So like when we're trying to figure out what proteins look like, we can get them to crystallize, so basically come out of solutions and ditch their water coats, take up some protein-protein contacts, and basically freeze in the same orientation in like over space, kind of like a brick wall but with proteins inside. And then we can shoot x-rays at them, and then the x-rays will interact with the protein and give out, change the x-rays, make them like scatter or diffract, and then we can work backwards from this pattern of spots that we're going to get, the diffraction pattern. And so I'm not going to talk about that today. Today I want to tell you more about the vapor diffusion methods that we use to get this crystallization to happen. So you might have seen, like, if you had like an ocean water and you got it like dried out, evaporated, the water evaporated and left behind like a crystal salt. So it's the same type of idea, except that we're getting proteins to crystallize. And so we take a drop containing a protein and a solution containing like precipitants, things like salts that are going to help the protein come out of solution, hopefully in the form of a crystal and not just like a clumpy aggregate. And so the idea is that the water is going to evaporate over time. So this is going to increase the concentration of the precipitant and the protein. And then the protein's going to run out of water. The water's like, because you're losing the water, and the water is what's needed to keep the protein dissolved. So if you get rid of that water, now the protein is going to make protein-protein contacts, hopefully in a way that will promote crystallization. So we get this to evaporate by sticking a drop containing our protein and the precipitants above so either on a ledge with sitting drop, so one of these little ledges, or like on a cover above a well in the hanging drop. This drop is going to be more concentrated, or in terms of the water, but less concentrated in terms of the precipitants. And in your in your reservoir liquid, that's going to be less concentrated in terms of the water, but more concentrated in terms of the precipitants. And the reason why I'm emphasizing water is because water is the only thing typically that's going to be volatile, so that's going to be able to evaporate and move between the drop and the reservoir. And so it's going to move from where it's highest concentration, so in the drop, to where it's lowest in the reservoir. And so this relates back to Raoult's law, which we were talking about yesterday, where actually what you're equilibrating, you're equilibrating the vapor pressure. So when there's more solutes, when there's more things dissolved, the vapor pressure is going to be lower. So the vapor pressure is going to be higher in our drop, lower in the reservoir, and so we're going to get the movement of water from the drop to the reservoir. You're removing the water, you're bringing those things closer together, and now you're promoting the crystallization. So let's look at a little more detail. So let me start by saying that there are many different crystallographic strategies, and there are different reasons to choose different ones. Some of them are easier to do at scale. So if you want to do a really, really big screen, which brings me to a second point, which is that you need to do a lot of screening, which is basically testing out a lot of different conditions. So different solutions, or what we call like crystallization cocktails, so different like mixes of different precipitants. So I'm not going to really talk about too much about the precipitants here, but these precipitants can be salts, so they can be things like polymers, like pegs. They act in different ways, and I have more on that in other posts, and I'm not going to really talk about that here. I just want to talk about kind of the idea of this vapor diffusion methods. So we can imagine crystallization. When we talk about crystallization, we can think of it in terms of a crystallization diagram. And so on our y-axis, we have our free protein concentration, and on our x-axis, we have our precipitant concentration. So for simplicity, let's just consider our precipitant is like a salt, and we have this salt, and we have our protein. What can get kind of confusing is that normally in other situations, we're talking about like solubility of like your salt or whatever, but here we're talking about solubility of our protein, and it's our protein solubility that's what we're caring about. If our protein is dissolved, that means it's not crystallized by definition, or at least the part that it's not dissolved is. You can have it some undissolved and some dissolved. But basically, when the protein is below the solubility line, then it's going to be in this undersaturated zone. So basically, the saturation is how much protein or how much thing that the water can hold, in this case protein. So each thing, like each solute, so things that dissolved, has its own solubility limits.
And so this line is going to represent the protein solubility limit. So if you're below this line, then your protein is not going to be crystallizing because it's going to be just in solution. So it's all making water-water contacts and then these water protein contacts that we need. If you go above this line, then things can start to happen. So initially in this metastable zone, you're kind of like in the middle. So crystals can grow, but they can't form. Then you have this nucleation zone where new crystals can form. And then if you go above this, then you have this decomposition line where you only have precipitation. So you only get the clumping. And so basically we need to get the protein. Our strategy with the vapor diffusion is to get this protein to a saturation. So when we're moving to the right, we are increasing the precipitant concentration. And how we're doing this in the vapor diffusion is we're getting rid of water. We're evaporating off the water. And so when we're evaporating off the water, we're increasing the precipitant concentration. When we increase the concentration of the precipitant, now what's going to happen is that the protein is going to be promoted to crystallize more because so you have less water and you have more precipitant. So this protein is going to have an increased concentration, both because you're removing the water and it's going to be promoted to precipitate more because it's hanging out with more precipitant. And so this is going to promote the nucleation of your crystal. So nucleation is basically where you get the start of like your seed of your crystal. Like basically the crystal is this orderly lattice, and in order to make that orderly lattice, you first have to have a few trendsetters that kind of go in and get things started. Once they're organized, then you can have the crystal can grow, and so the proteins can then add on. And so once you're in the nucleation zone, what's going to happen is you're going to start getting less free protein. So initially our protein concentration was going up because we're removing water, but this is our free protein concentration. And so basically we are now going to have, it's not going to be free, right? If it's joining this crystal. So now we're moving down into this metastable zone. And when we're in this metastable zone, then the crystals can grow, but they can't form. And then eventually we're going to get to an equilibrium where the crystal, there's no more crystal, they're going to get this like dissolved, undissolved equilibrium where you're not going to get more of your crystal's not going to grow anymore unless you change something. So we have two equilibriums in play here. We have the drop reservoir vapor pressure equilibrium, which is what is going to be driving the water to leave. And we'll talk about that more in a minute. And then we have our dissolved, undissolved protein equilibrium, and that's going to be the up and down. So we have to do a lot of like troubleshooting and screening and stuff to try to find the right initial conditions, because then we can't really control easily what's going on after that. It's going to depend on like the temperature, which we can't control, but then a bunch of things, and it's just basically too complicated to try to like map it out, and there's all this like randomness and stuff. So we try a bunch of different conditions, and it's important to try these different conditions because if you have too much or too little of something, you have too much precipitant, you're going to get lots of small defective crystals, or you're going to get precipitate. But if you don't have enough of your precipitant, then you're not going to get any crystals. And so you have to do a lot of screening to try to find the right conditions. And I have more on that in other posts. So we need to keep in mind the things that we have in play. So we have in our crystallization experiment, we're going to have a cocktail solution, which is going to contain the precipitant and the water, and then we're going to have a protein solution, which is going to contain the water and the protein. And then we're mixing these together and to get our initial drop solution, and that's going to be in this drop that we put in here, which is where the crystal is going to grow. Sometimes you see this liquid called mother liquor, the liquid that's surrounding the crystal. And then we have this reservoir. And so the reservoir doesn't have to have the same exact stuff as the drop. Well, it doesn't have the protein because the protein's non-volatile, so the protein can't just like come up and join the drop. If you want to add more protein, you have to manually go in after it's started and then add more. But the reservoir, commonly what you do is you just add the same thing that you added to your protein, except because you're not adding the protein solution, your concentration of your salt or your precipitants or whatever are typically on a molar level going to be much higher than the protein. And so when we talk about the concentrations, it's kind of all relative, and you're adding a lot of water in your protein solution. So when you mix the two of these, now you're going to have a more dilute solution than what you put in. And we can put this in, we put this drop either hanging from the top of a well. So we can do these in different size wells, but I'm just showing you these are the 96 wells. And so here we have the drops on these top of this plate. So here, and when you do it on one of these, like this is on a plastic screen. But when we do it with these little like discs, and then when we do it manually, we have like grease around the wells, and I'll show you that later. For example, like this. And then we put our drop on the top of this glass slide when we're preparing it. We flip it over, and now it's on top of this well. Your drop is going to be more dilute in terms of your precipitant and it's going to be more concentrated in terms from the water's perspective, because in your reservoir, you're going to have this super duper high concentration of these precipitants and stuff. So the water is going to be kind of like diluted out. So although you have a lot more water molecules, because I mean, it's like a pool compared to a drop, the water molecules now have to be like, they're diluted out by all this precipitant. So when we talk about the movement of the water, it's going to be from the drop to the reservoir. And we'll see how this relates to water vapor, to vapor pressure. So vapor pressure can be a kind of confusing concept, but the key thing is that when things evaporate, the more evaporation you have, the more vapor pressure you're going to have. And so when the water is evaporating, so when it's going from a liquid to a gas, in order to do this, it has to be on the surface so that it can escape as a gas, because it's basically kind of stuck where it is because there's a bunch of water molecules. But if it like randomly or whatever gets enough energy to kind of overcome those attractions to other water molecules and is at the surface, then it can escape as a gas. And so the amount that it can do this is going to depend on the strength of the interactions between like the water molecules, and if the temperature and the pressure that's on top of it. When the water molecules do evaporate, then they're going to put pressure. They're going to build this vapor pressure. So you can think of there being pressure above the liquid, and this pressure is going to be like competing against the external pressure. And so it's going to be hard for the water molecules to like totally escape, and they're going to get pulled back down a lot. And so they're going to condense, and you're going to reach this equilibrium between the evaporation and the condensation, where you have when you reach that equilibrium, you're going to basically have some set vapor pressure, what's corresponding to like the amount of evaporation. So how much like gaseous water there is. So more evaporation, higher vapor pressure. So what's going to happen when you add a solute? When you add a solute, now basically you're kind of taking up some of the surface real estate, and you're increasing the entropy of the solution, making it less of a benefit to become a gas. And so basically entropy is randomness or disorder. And so there's a lot of different, this is a more random solution. If you have a lot of solutes, you can have a lot of more different states and that sort of thing. And so you're going to have decreased evaporation because you're having the surface stolen, and you are having this increased entropy. We can talk about this in terms of Raoult's law. If we want to get all like mathematic about it, it's basically just saying that the amount of this vapor pressure lowering is going to be dependent on the number of dissolved molecules. And so it's a colligative property, or the number of dissolved particles. So it's a colligative property, so it depends on like the number of things you have dissolved in there, and not the identity of them. And so this is an idealized, Raoult's law is like ideal conditions. And so you can have deviations, and so basically if the new bonds you form are stronger or weaker, then you can have deviations. More on this in yesterday's post if you want to know more, but it's not quite as simple as just number of particles, especially when we're dealing with things like macromolecules like proteins and stuff. So I'm not going to go into that too much, but I do want you to understand this concept that the more evaporation you have, the higher the vapor pressure. So if you have a higher vapor pressure, we're talking that's going to correspond to having more of it's been evaporated. And if you have a high pressure, then things are going to go to the low pressure. And so when we have this high vapor pressure in our drop, because our drop has less of the solute, less precipitants in our drop. And so it's going to have a higher vapor pressure. So in our drop, we have less solute than we do in this reservoir. So what's going to happen is you're going to have more evaporation from this drop than you have from this reservoir. What's going to happen is because you have this water evaporating, you're going to have a bunch of high vapor pressure around the drop and lower around this reservoir. So what's going to happen is that these water molecules now, they're going to go from their high pressure to the low pressure. And so they're going to diffuse out of the drop and into the reservoir. When they fly down to the reservoir, they're going to get sucked in and they're going to condense and become water. But you're going to reach an equilibrium where you have equal vapor pressure throughout. So at the start of the experiment, you have a higher protein concentration in your drop, and at the end, you still have a higher protein concentration in your drop because the protein's not moving. You're going to have a higher vapor pressure in the drop in the beginning, but at the end, you're going to have the same vapor pressures in the drop and in the reservoir. You're going to have a lower precipitant concentration in the drop to begin with, but at the end, you're going to have equal concentrations of your precipitants. And then your reservoir is really not going to change that much, except for how much vapor pressure there is. But in terms of composition, what's happening in your drop is going to be a lot more dramatic because you have this smaller amount of liquid. And so if a little bit leaves, it's going to be a big deal. In your reservoir, it's kind of like adding a drop to a pool. So if you add a drop of water, it's not really going to change much. And so the effects are more dramatic in your drop, and that's where your protein is. And so that's typically what we're focusing on. But this reservoir is important because its high precipitant concentration is driving this vapor pressure difference that's going to lead to the evaporation out of your drop. If you were to start with them equal, now there's not really, you'd be at equilibrium basically when you start, and so you wouldn't get the evaporation out of the drop. You'd be getting equal like evaporation back into the drop, or be equal like evaporation from the reservoir back into the drop. And so this is why we do it this way. And so for example, your vapor diffusion experiment, you might start with like a microliter of a protein at 5 mg per mil, and then a microliter of water, and then your precipitant at 1 molar. And so you would mix these, and then you would mix the, so your precipitant and your water, and would be your cocktail solution, and then your protein in your water is your protein solution, to get your initial drop solution. And so here you can see that the cocktail solution, your solution of precipitant, is going to be half the concentration as the concentration in the cocktail solution alone, which is what you have in the reservoir. And so at the end of the experiment, you're going to have roughly equal amounts in the reservoir and the drop in terms of your precipitant concentration. You're not really going to change the volume of the reservoir because it's just like a drop in a bucket, but you're going to have a lower volume in your drop, and hopefully you're going to have your protein be crystallized. And so you're not changing the amount of the precipitant, you're not changing the amount of the protein, but what you are doing is you're increasing their concentrations. So we talked about in terms of the vapor pressure equilibrium, that can be a kind of confusing concept. So sometimes it's easier to think of things like just in terms of concentrations of the water. And so we can think about it in terms of the water diffusing from where it's a high concentration to where it's a low concentration. The complicating thing about this is then you could get confused because, okay, well, we're starting with a high, we're going from a low concentration to a high concentration of your precipitant, but it's the solute that's the thing that can move. So in diffusion, you have basically the movement of something from a high concentration to a low concentration on net. And so basically these molecules are moving around randomly, but if you start with a bunch of them over here and not many over here, a bunch of them over, they're all moving randomly, but because you start with so many over here, you're going to end up with them evenly dispersed. And so it's going to be like it's moving from like it has a drive to move from the high concentration to the low concentration. So you can think of it intuitively as kind of like the water is moving from the region where there's a lot of it to the region where it's high concentration to the region where it's low concentration. So you can think of it kind of like going to dilute out the reservoir solution. But you have to remember that it's the solvent that's moving here. And so this can be a kind of confusing because normally when we think about diffusion, you're thinking about things like putting a drop of dye in a liquid, right? And then the dye is like moving out. But here we're moving the water because the water is the only thing that can move. And this is why because the water is the only thing that's volatile. And this is the reason why the water is going to move out of the drop from the reason where there's higher water concentration to lower water concentration. And so concentration, remember, is like we're adding more other stuff. So when we're adding more other stuff, there's going to be less water in there. And so this is where, so with Raoult's law and stuff, what we're talking about is we're talking about the mole fraction of the solvent and in terms of the particles. And so the more things that we add to it, the lower the mole fraction of the water. So the more the water is getting diluted out, and it seems like there's kind of like less. If you were to take a drop of water, the same size drop of water from each, you would have less of the water in the one with the in the reservoir to begin with. It's important to note there are also lots of other crystallization methods. So one of them is there's this thing called like batch, or basically with batch instead of diffusion, you're kind of guessing you're kind of hoping that you get the right situation in the very beginning. So you're like aiming straight to this point where you're trying to go gradually with this evaporation in this vapor diffusion method. With the batch, you do it like under oil and stuff often, and so there you don't get any diffusion. So basically you're trying to mix them to get to the like point at which this is already here, whereas with the vapor diffusion we're gradually getting there by losing water. And so batch can be done at like really high scale and high throughput. I've never done it personally. I've only done vapor diffusion. There are also like some liquid diffusion methods and dialysis and stuff, which I'm not going to talk about because we're just going to talk about vapor diffusion. And with that, there are these two main methods, which are hanging drop and sitting drop. So there's some things to consider in both of these different methods. So in hanging drop versus sitting drop, the concept is the same, that you're having the movement from the vapor diffusion movement. So you're having the movement of the water out of the drop, increasing the protein concentration and the precipitant concentration, and promoting the crystallization, or at least promoting them coming out of solution, hopefully as crystals. But there are some differences between hanging and sitting drop, and these differences are typically in terms of they're going to affect how quickly the the evaporation happens. And so if you have really quick evaporation, you're going to go quickly. You might be going too quickly that you're going to basically form your protein's just going to clump up, or you're going to get a lot of nucleation events and lots of little crystals. And so if how would you get faster? So the diffusion could be faster, the evaporation could be faster if you have a hanging drop often, because what's going to happen is if you think about where you have a drop versus where you have it in like a well, so the well can be on like a ledge, or it can be sometimes like in the center, there's like a little pedestal. But in those cases, basically you have a larger surface area than in your sitting drop, where basically it's kind of like if you had an egg yolk with your hanging drop, and now with your sitting drop, you basically have like your egg in a little egg cup, and so there's less area available, and the surface area is where you're going to get the evaporation from. This can be even more of a difference if you have like surfactants, so things like detergents in your solution. That's going to increase, it's going to decrease the surface tension and increase like the adhesion and stuff. And so basically your drop's going to get spread out more, which is going to give you even a greater surface area. And in these cases, you're going to have really fast evaporation, which can cause those problems. So there are different reasons to choose one versus the other. Sometimes sitting drops can be better for like automation and stuff. There's various reasons for different things. And a lot of it's going to come down to like what you have access to, what people in your lab normally use, that sort of thing. With any of these, you can do them at a bunch of different scales. So with different size plates. And so these are the 96 well plates that are we can use with our like mosquito robot I'll show you in a minute to help. And these are, I typically use those for screening to try to find the right conditions. And then when I was doing crystallization to actually get crystals to get structures and stuff, do it manually with these bigger drops that you have to set up manually, so it takes more work, but you can get bigger crystals and they're easier to fish out. And so you're going to do a lot of different screening to try to find the right combinations and concentrations. So you're testing things like pH, different precipitants, different salts, maybe some additives, various things. And there are a lot of different screens you can buy and you can mix yourself. And then you can have a robot help you set them up. And so this is how this works.
In this video, you can see the mosquito at work. So first it's taking protein out of the wells and it's adding drops of it to the top of like the stickery-like membrane that we're going to put on top. Now it's taking liquid from the reservoir. So this is the liquid with the precipitants and stuff. So like the salt, pH stabilizers, the pegs, all of that sort of stuff. And so it goes column by column. So you can have different things in each column. And it's adding a drop of that to the drop of the protein. So now you're making a more diluted drop containing your protein and the precipitant mixture.
Afterwards, you stick it on top of the reservoir that has the precipitant mix. So that's how the robot helps us. Here's how I do it manually with these. I basically set up my drops. There's this like little plate that helps. So it has these are just glass cover slides. And then you have these wells that have this rim of like this grease around them to help the lid stick on, but so that you can more easily get it off. So with those, one of the things with the robot is that it's like really hard. You have to like kind of use a X-Acto blade to kind of like cut one of those pieces out so you can fish your thing out, and then you have a really tiny drop, so it can be kind of hard. But when you do it manually, you can make these bigger drops, and you can flip these over with tweezers and then stick them on top of the well. So it takes some practice just to kind of like, you don't want to let it evaporate before it gets over the well, and you want to make sure you seal it well, but don't like break it. So yeah, but basically then you can just set up your next row, and on and on and on. Then we typically have to wait and see if we get crystals. And so to help us see this, we have this robot, another robot. So this is our like crystal hotel, our plate hotel, where we can store the plates. And then this robot is going to take the plates on, like, we schedule it. So we tell it like how often we want it to take pictures, and then it's going to take that plate and take pictures of it. And then we can look through and see if we find crystals or if there's nothing there. And so hopefully then if we see that there's a beginning of a crystal or something, so typically we don't want to mess with it too much because we don't want to change any conditions and make it so that it doesn't crystallize. And then we can take it out and look at it further under like a manual microscope and see pretty crystals. Hopefully. If not, it's back to the screening. So hope that helps you understand vapor diffusion crystallography method.